All right, so we can go ahead and get started. So today we have a few cool things to go over, mostly related to how to motion plan through obstacles in our environment. So dealing with the collisions in a scenario where we don't want to hit anything. So in class, Zach has been talking about how to plan through contact and like this hybrid motion planning stuff. And you'll do this in your last homework 4, which goes out next Wednesday. But what we're talking about today is how do we motion plan? Like, how do we solve these trajopt problems or find some feasible plans that actually take us through the environment without hitting any of the obstacles? So, and I'll also add one other thing that I noticed that Zach went over that may have confused some people that may be useful for your projects. So 331. Okay, so the first thing I'm going to go over is the L1 trick. So the L1 trick is how to deal with convex problems that have cost functions that have non-smooth elements in their cost, specifically an L1 norm. So something that you've seen Zach do in class is he approximated the friction cone. So, this L2 cone, and he approximated it with an L1 cone. And the way he went about that is like a little complicated. So I'm going to kind of go through that in like a different approach. And if you prefer his way, it's fine. If you prefer this way, it's also fine. But it's just kind of two different ways to go about doing this. But it's a super useful trick in practice. When we write down these convex problems in convex.jl, all this stuff happens behind the scenes. But if you're going to implement something like, and you want real speed, you want to actually implement it directly in a solver. And this is how you do that. So what we're talking about is a problem where we do minimizing over some f. And I have some smooth cost f of x. And what I'll do is I'll add just like an arbitrary constraint. I'll just say I have c of x equals 0. So now what I'm talking about adding is that say I added something like this. And so what's super common is to do L1 regression. So I'll say, I'll add this thing. And what this is doing is that this is putting a penalty on the L1 norm of x. And remember, the L1 norm is just the sum of the absolute values. So if we think about like, what this is going to minimize, it turns out this is a pretty close approximation for what's called the nuclear norm. So this is just like a fun little tidbit, but x, the nuclear norm, and this is the number of non-zeros. So this is not super important, but the L1 norm is a nice approximation for the nuclear norm. And what this means is that if I throw an L1 cost in there, it's going to encourage sparsity in x. So if you imagine, if I could say, here's a good example of a problem like this. I'll do, so say I want to find the minimum L1 norm x such that ax equals b for an underdetermined linear system. So there's an infinite number of solutions of ax equals b, and I want to find the one that has the minimum L1 norm. What this will end up looking like is this will give you like this x, and it'll have like, 0, 0, and then some value, 0, some value, 0, 0, some value. It has a bunch of zeros in it. So when we put this L1 norm, we're encouraging sparsity, which ends up being super useful in a lot of cases. So if I'm trying to do some sort of like feature analysis, I'm trying to see like which features like really matter the most, I can put like a nice L1 regularizer on this, and it will like just in the background encourage as many zeros in the solution as possible. So you'll see this all over. This is also common for fuel costs. So if I want to minimize the amount of fuel I'm using on like a spacecraft or something, I'll put an L1 cost on it. This is what they actually do. And what it'll do is it'll encourage minimum fuel usage. And so you'll get these like impulsive maneuvers. So like it'll fire, then it will do nothing. Then it will fire again. Then it will fire again. So the idea is that like when I add this L1 cost, I encourage sparsity in the solution, which can be useful for a lot of different things. So now the way that we do this, move this over. So the way that we do this is super simple. So I'm going to add a slack variable called t. So add a slack variable t. And now I'm just going to solve the following problem. I'll do min x and t f of x plus 1 transpose t. And this is just This is the same as just me summing up t. And then I have my normal constraint, which is just c of x equals 0. And then now I have to deal with this t. So I say that t must be greater than or equal to x. And t must be greater than or equal to negative x. So this will take a second. You'll have to like write this down to like commit yourself of this. But basically what this does is that I'm trying to minimize the sum of t, right? This is in the cost function. And I constrain t. I say t must be greater than positive x, and it must be greater than negative x. So what that means is that t is going to lock down to the lowest value that it can, which is going to be the absolute value of x. So if you imagine if I had, if I had an x that was like, say my x was, 1, -2, 3, 4, this kind of thing. My t is going to lock down to the lowest number it can, right? Because I'm trying to minimize t, but t has to be greater than the positive or negative of all these things. So t would end up being 1, 2, 3, 4. Let me make it more interesting like that. So t is always, if I set up the cost such that I'm trying to minimize the sum of t, and I add this constraint here saying that t must be greater than positive x and greater than negative x, the solver is going to pull t down as low as possible, which is right on the absolute value of x. So what we have here is that we introduce this t, and this t ends up being a vector that is the same length as x, and it ends up just being the absolute value of each component. Then I sum those up, and that's what the L1 norm is. The L1 norm is the sum of the absolute values of the vector. So just like this, I went from having a non-smooth cost function. So, when I take the gradient of this, I get a subgradient here, which is not always good, and the Hessian information is useless. So what I want is like a smooth constrained problem. And this is a trick you'll see all over optimizations. We can convert these cost functions that are non-smooth into smooth cost functions by adding a few more constraints. And this is normally the way to go. So in this case, I had just one normal constraint, then a non-smooth cost function. Now I have a nice smooth cost function, right? This is just linear. That's totally fine. And then my constraints, I just added 2 linear constraints, which are easy to deal with. So this is like kind of the element story. So the way Zach did in class is a little different. I prefer doing it this way, but you're more than welcome to use whichever way you want to. I just figured that this is like a useful trick. That it'd be cool for you guys to see it like one at a time. Yeah, and then I'll just make one note about how useful. So useful for encouraging sparsity. Identifying important features, and then min fuel actuator number use. And then something to look up is something called the lasso problem, which is like a stats thing. It just basically has L1 regularization in the regression problem. So this is the L1 story. Definitely worth knowing, especially in controls. So now let's talk about stuff with collisions. So avoiding collisions, this is obviously a super important part of robotics. And now we're going to take a look at just an example case where you might use this. So I have some world frame. And then I'm going to have some I'll have like a little Roomba. So this is like a little differential drive robot. And I'm going to have a few obstacles. And the idea is that I want this Roomba to do kind of this kind of thing. Okay. So the idea is that how do I bake in these constraints into the motion planner such that this thing does not hit it? And so there's a bunch of different options for this. This is like, one of the most studied parts of robotics, because as you imagine, this shows up all the time because real robots have these collisions they have to avoid. So what I'm going to do is I'll detail three generally common ways that people deal with these things. And, maybe this is something that you'll use in one of your projects. So first way search-based, sample-based planners. So what I mean by search-based, I mean that I can use like graph search or tree search. And sample-based, I mean, so I'll write down some examples. So this would be like, if I already have a predetermined grid, so I have like a grid of all the possible states and I want to find like a collision-free path. So if you imagine this is how like a maze would work. This is where I'd use A star. A star if the grid exists. If there's no grid, so it's like just a big state space and I haven't discretized the states already, which is very common, I could use RRT. And then there's also RRT star. And these are, so this is search. This is sample. So these are both super common. They work for very hard problems. So if you imagine if I had something like, I need to get a robot through a maze, you would use one of these things and you could find a way through the maze where the ideas that we'll talk about next would have like an insane amount of trouble doing so. So these are like the highest powered, most expensive ways to find a collision-free trajectory between point A and point B. Also, yeah, everything I'm going to talk about here is like NP hard. So these are these are problems that people will solve in practice in real time. But you should have like an understanding that like these things are not guaranteed to find a solution in any set amount of time. So this is like, always goes back to the importance of trying these things in sim, then trying it on hardware and seeing like what your actual timing stuff looks like. So that is search-based planning. So both these topics, A star and RRT, are like, there's a million resources for it. And it's definitely worth like having a good understanding of these as like a general like robotics person. And I'll just give like a quick layout, I guess. So for A star, imagine if I have like the states are already discretized in some nice grid. I just solved like a search problem with some heuristic that gets me through here in like a collision-free path. And this is A star. RRT works totally different. RRT is a sample-based planner. So what it does is it just like samples a bunch of states and tries to connect them. So it's like, it looks like a bunch of growing trees. So these trees all kind of grow out as I sample, and then it's going to connect the first feasible path it finds and be like, boom, done. I found a feasible path. These resulting paths are not going to be smooth. Like the resulting successful tree may like look like this, but it will find a collision-free path if one exists, if you sample exhaustively. So as you imagine, these things are great for planning. So finding like just like the positions that get me from point A to point B without a collision, but this is not optimal, right? And so RRT star is kind of like in addition to this. And RRT star, it does like this nice, I guess, smoothing, if you will, of the feasible trees in RRT, and it kind of smooths out the trajectories. And in theory, if you run this thing exhaustively, RRT star will actually recover the optimal collision-free path between point A and point B. So this is a story for search-based planners. We won't do this in this class, but you will see this all over robotics, and maybe you've taken a class on this. So I know there's like the planning class by Maxim Lakachev here at CMU is super popular, and I'll go through all these. Second thing is control barrier functions, or CBFs. And you will see this kind of everywhere. They have been big in like the last 10 years. And let me just pull up a quick thing I have prepared for this. Sweet. So the way control barrier function works is that it's a control modifier. So I'll write it like this. So the way control barrier functions work is it's just, so not the control barrier function, but the resulting control policy looks like this. I have FCBF, and it's going to take in a control input U that comes from some other controller. It's going to take in a U that may or may not be safe, and it will return a safe U. So it's going to modify the control that comes in. So you can think about this as basically it's filtering your actions to be safe actions. And it's pretty cool how this works. So the way this works is that I have some safety index. So over here, do CBF. So I have some safety index. It's a function of the state. And the idea is that I want this thing to be less than 0 for safe. You will see many different conventions here. So the papers by Aaron Ames are like the really popular ones. I think he uses safety index being positive as safe. But what I prefer is a different paper. Someone here at CMU that'll put in the recitation notes. And just for the convenience of consistent notation, they use safe is -0. So basically I have some phi function. Phi is going to take in the state, it's going to tell me like how safe it is. And if it's negative, it means it's safe. If it's positive, it means it's unsafe. So I'll give an example of how to write something like this. So imagine if I would have phi equals, and I could do something like this. I could do negative norm of R robot minus R obstacle. And then this would be, okay, so first let me write out just the general, what we want, and then we'll convert it to a safety index. So what we want is that we want the norm, the distance between the robot and the obstacle to be greater than the radius of robot plus radius obstacle. So this is just saying that if I approximate everything with spheres, so I assume I have a sphere around the robot, a sphere around the obstacle, I can write down this function that tells me like, am I hitting this thing, right? Are these two spheres in contact? If they're not in contact, then the distance between these two is greater than the sum of the two radii. If they are in contact, then this distance can be less than that. So this constraint right here, this is my safety constraint. So I want this distance to be greater than the sum of these two radii. So now let's convert it into this form where if it's safe, it's less than 0. So let's just move, let's just rearrange this inequality. So let's do go ahead and rearrange this. Minus 0. And now this is my safety function. So you see how I started out with just what is my generic safety constraint? I just rearrange it such that it is consistent with this definition of what safe is. When phi is less than 0, it's safe. When it's greater than 0, it's unsafe. So this is my control barrier function. So you're going to see CBF drawn everywhere. The actual barrier function is this right here. This is like my safety function. So then we think about like, well, what do we have to do for a controller to make sure that all the trajectories stay inside this safe region? And so the buzzword that you'll see is the following: forward invariant. So what forward invariant just means is that when it comes to a set, I have a safe set of actions. So I'll do here's unsafe. And I have, some safe set. The idea of forward invariance just means that once I put my system inside the safe set, it'll always stay inside the safe set. So forward invariance just means that once it's in the set, it's going to stay in the set. So the whole idea with control barrier functions and the math behind them is that I want to modify my control inputs such that assuming I'm already in the safe space, once I'm already in the safe set, if I just keep modifying these actions in a certain way, I will always stay in the safe region. And this is like, there's a huge amount of math that they dress this up with, but this is like the main idea of forward invariance is just once I'm in the set, I'm staying in the set. And so what does this actually look like? Well, it looks like the following optimization problem. So we have, if you remember, I talked about how F, CBF. So I'll have U naught, and U naught, this is going to be my nominal control input. So remember, CBF is not a controller on its own. It's just modifying the controls. So the real control has to come from something else. It could be, could be a trajopt solution. It could be LQR. It could be generic feedback control. It could be anything. I'm going to take in some control, U naught. I'm going to modify it such that my dynamical system is forward invariant inside the safe set. So it stays in the safe set. And what this function actually is it's the solution to the following optimization problem. Arg min U. I'm just going to find the closest control input to the one they gave me, such that, then let me make sure I get the signs right here. Phi dot is less than lambda phi. And then a few notes on this. So one is that lambda should be negative. And two, phi dot equals the gradient of phi with respect to x. Is the dot product of this with the time derivative of this. So if you imagine if x dot equals f xu, so these are my continuous time dynamics, then this phi is just phi dot equals nabla phi x transpose f xu. So what you'll run into sometimes, and a good example of this is with a double integrator, what you'll run into sometimes is that forming this thing is a little weird because sometimes it needs time to actually make a difference. So if you imagine the double integrator, I have a position and I have a velocity. That's my state for the system. And my control is the acceleration. So I at any instantaneous time, I am directly affecting the velocity, but I need to integrate it some amount of time for it to actually affect the position. And so if you're at the math, and I'll like post an example of me doing this. If you go and do this, you'll see that if you just do this naively and just write down like the double integrator dynamics, you get phi dot is always 0, which is not true. So like a little kind of workaround here is that you can just do is approximately. Actually, I'll do this. I'll say x dot's approximately. So x dot is approximately. I'll do f. So here's my discrete dynamics function. So I'm going to be integrating it. X u minus x over dt. So I can approximate this thing using this right here. So f discrete minus x. So I'm just like, x2 minus x1. So I take a step, difference it, divided by dt, and this gives me my approximate x dot. And for things like the double integrator, this will capture the influence that the acceleration has on the position, and it actually makes everything work. So you can approximate this, and then you will have to linearize. You'll have to linearize f discrete if it's a nonlinear system. Okay, and so one important thing to note here is that assuming that this f discrete is always linearized, which is totally reasonable given our like very small time steps that we normally take, this problem is always going to be convex. And the reason why is because phi is a constant, right? Like we're minimizing over u. Phi is just a function of the current state. So this is in the sense of the optimization problem, this is a constant. Lambda is a constant, and then this function right here is going to be linear in u, because I'm linearizing this thing right here. So I linearize this thing with respect to u, and this gives me this constraint right here is going to be linear in u. It's a linear inequality in u. And then this cost function is nice and convex. Now, another thing to note is that if I have multiple different objects in the scene, so like the example I drew up here, I have 3 different shapes. This little safety function I wrote down right here, this was for one of the shapes, but I can do this for all 3 of the shapes. And what I do is I just create a new safe function for each of these shapes. So that if I want to start adding stuff, I'll just do the following. I do 1, 1, 1. I can add the second one. And I can just add as many safe functions as I want to, and the control barrier function will just deal with it. So this is a super fast, nice QP. And I guess the main benefit of this control strategy is that I can effectively take a super naive controller and I can just modify it by pushing it through this control barrier function stuff, and it will output a safe controller. So it can often be a really cheap and inexpensive way to solve this control problem in a safe way. So doing general, like all the RRT stuff could be super expensive. If the problem's not that complicated, you can probably get away with doing something like this instead. And, you know, in general, you should do the simplest thing possible. And oftentimes this can be the simplest thing possible. So this is kind of like my crash course on control barrier functions, super brief. I'm going to put up some code. Maybe I'll go through it at the end of this, and I'll kind of walk through like how the code works, like how this actually works in practice. And I'll do it for a double integrator, like avoiding a sphere.
I have a question about the control barrier functions. Are there any side effects to modifying the controls? Because in class, Zach demoed that, say for LQR, he showed that if you do some naive modification of the controls, like if you just clip them, for example, to respect some constraint dynamics, then LQR is not going to do the optimal thing. I know control barrier function is not exactly like as naive as clipping it, but like, are there any effects from that?
Sure, yeah. So this is a super good question. So in general, nothing. So what Zach talked about in class was, I think he was doing ILC, and he was naively just clipping the feed forward plus feedback terms of the control. And the issue there, and you guys had like a quiz question on this, is that if I take the LQR solution, so say I have a control problem, I have actuator constraints, so I have limits on U. If I take the LQR solution and just clip it, what I get is not optimal. It is not the optimal solution for the constrained control problem. And so this is true in the stuff that Zach did, is that he starts clipping it, and now all of a sudden what you have is not optimal. But if it's not optimal, it also means it's not stable. So the whole benefit of LQR is that it's going to give you a stable controller. If I start just like removing parts of the optimality, I could potentially lose the stability. So yeah, in general, if you're ever modifying your controls, you should like always be on high alert, because there's a chance that you do something that like makes this thing unstable. And so this is totally true with control barrier functions. The same, right? It's not as naive as clipping, but oftentimes what people will do is that they'll add, let's do this. Oftentimes people will do the clipping in here, and how safe this is totally problem dependent. So some problems, this is totally fine, they're not a big deal. What Zach was doing was like a cart pole swing up, which is like a very under actuated system. So there, like when you start clipping and modifying those controls, it makes a really big difference on the performance of the system. But this is not always the case. But yeah, this is a super good point you just made. Whenever you're modifying controls, you should like be careful, because any guarantees you have from the original controller, as soon as you start modifying them, you're going to lose those guarantees, right? So it's no longer going to be optimal or anything. This is like basically a hack that we throw on top of our controls to make them safe. Sometimes it works super well, but sometimes it's not the right tool for the job. Does that answer your question?
Yeah, that makes sense. So then I guess that means before we use control barrier functions, we have to verify this. How do we verify it?
So this is all just done in sim. So what you do is that like, I have some controller, I say it works really well, but okay, it looks like I'm like hitting my, like I'm violating some control, I'm like violating some safety concern I have. I would put that into a control barrier function. I would just run a Monte Carlo where I just do tons and tons of samples. I just try it from a bunch of different interconditions, and I make sure that the controller is still performing like nicely. And oftentimes for like a well actuated system, this is not a problem. It will act just fine. So yeah, unfortunately, like as soon as you break out of the nice linear convex world, so like pretty much anything other than LQR or like convex MPC for like linear problems, we run into this problem that like the only way to truly verify this controller is just exhaustive testing. And this should be done like with everything. And like in reality, like, you know, if you go work at a company that does control stuff, you'll see that they will like in extremely exhaustive fashion, they will sample like the living daylights out of your controller, and they will run it through everything to make sure it's like all right when it's supposed to be. And even then, sometimes like stuff gets through. So yeah, this is like the non-convex, non-linear world is that we're like really short on guarantees.
And so, okay. Okay. So yeah, this was a question. So like, there's no formalized way to kind of have those guarantees. We are just bounded to just test
So
extensively.
I guess this is like, so there's a class, I think it's taught in the spring here, Safe Control by Cheng Lulu. I took it a few years ago. And this is like a super active research area. And I guess what it all kind of boils down to is that there's a few types of systems with a few types of controllers where this is like in like a nonlinear, non-convex regime where you can make guarantees. And this is like a super hot research area because like, wouldn't that be great if I could write down this like nonlinear system with a nonlinear controller and just like have the same confidence that I have with that as I do with LQR. But it turns out it's like, this is very difficult. And this does not generalize to every single system. So if you like this stuff, you should go talk to Chenglu and you should take her class. It's super great. And it gives you kind of like a rundown of a lot of these things. And in fact, the paper that I'll post about control barrier functions is from her and somebody else. And they go through and they do a really awesome job of unifying a bunch of these popular safe control methods that come with some guarantees. And it kind of throws all of those ideas into the same framework with all the same notation, which is like a super nice crash course to go through and learn all these things. But yeah, guarantees for nonlinear control are like slim to none, but they do exist. And it is a big research area, but you should not count on it.
Okay, perfect. Thanks.
Sweet. So now I'm going to wrap up.
Hey, Kevin.
Yeah.
Is there no way that we can just use this cost function and these constraints while solving the original QP for getting the optimal control?
Yeah, you totally can. So this is what's coming next. So what's coming next,
okay.
I'll talk about like holistic motion planning where I consider these constraints, right? Because what I'm doing here, this is not optimal. Whatever the original controller was may have been optimal. Like, so say it was, say the original controller that's producing this U naught, say it did come from some super sophisticated trajopt regime where I'm solving, with real optimality conditions here for the optimal control. Once I go and modify this, it's gonna change. It will no longer be the optimal path because the original formulation is not considering the collisions. And that's often because these collisions are really challenging to put into nice constraints. And this brings us to the next thing we're talking about, which is the third approach. This is motion planning with collisions. All right, collision avoidance, because I feel like it's important to make the distinction between like planning through collisions. So like, hybrid motion planning with contact. And what we're talking about today is just collision avoidance. So this is, I have a robot that does not want to touch the environment, right? I'm not doing any sort of like manipulation or like contact planning or anything. Like I don't want to hit anything. So, a drone like doesn't want to hit stuff. Like you may have like a Roomba that doesn't want to hit like walls or whatever. So this is for collision avoidance. And what we do here is that we're going to have the same sort of kind of safety function stuff I described before. I'm now going to describe in a more generic, just what is my collision constraint? So what I'll do is I'll say the following. So I'm just going to have, I won't call it phi, I'll call it something else. I'll do, I guess I'll call it C for lack of a better thing. So C is just going to be my collision avoidance constraint at each time step X. And what this will do is that now I have to make a decision. How do I want to describe my robot? And how do I want to describe the object? So far and away, the most popular way to do this that is not that great, but it's super popular, is just approximate everything as spheres. So this is kind of stuff I wrote earlier. I'll do right here. So I'll do, this is some like R robot. And this thing right here, this is R obstacle. And you remember this constraint that I wrote down right here? This is the same thing. And I'll just do a little rearranging. So this is my collision avoidance constraint. And so what you'll see is that it is often very like annoying to differentiate through norms. So a very common way to do this is that before I rearrange the inequalities and everything, say I just squared both sides, which I can do. This is the same as me doing this. So this is I guess a nicer constraint that you'll see. So imagine if I just squared both these sides. So if I square both these sides, it just makes the constraint a little nicer. This is a tip I gave you in question 3 of the current homework. So now motion planning with collision avoidance, I have this constraint here, which is nice and smooth, but it's non-convex. Collision avoidance constraints are always going to be non-convex. There is no scenario where these things will be convex. And the reason why is pretty simple. So imagine if I have a state space. This square is my state space. This is convex, right? Convex just means that any 2 points inside the state space, if I interpolate between them, it's always in the state space. So I choose here and here, anytime before this is convex. As soon as I say there's a region here you can't go, it's now non-convex. So this constraint that says, stay in the black but don't go in the red, this is non-convex because you imagine if I took this point and this point, these are both feasible points. But if I interpolate between them, I go through a region that's infeasible. So this is non-convex. So it does not matter how you write this down, the collision avoidance constraint is always going to be non-convex. And this is one of the main reasons that like CBFs are so popular, is because a CBF is just, I solve an LQR problem or a nice MPC problem that I have, guarantees of like how long this will take. This is like I can do this in polynomial time. I can solve a convex MPC problem, or I can use LQR. That's easy. That'll run the same time every time. And I just pushed over to my control barrier function, solve a nice little QP, spits out a new control, and everything in that like pipeline for the control is very predictable in terms of how long it's going to take. And the reason that we don't go through and solve the whole problem all the time is because these collision avoidance constraints are non-convex. And this turns our problem into a much more challenging one. Not impossible, still totally doable, and people do this all the time, but it's difficult enough that using the vanilla controller plus CBF is still pretty popular because this is hard. Okay, so how would we solve like a motion planning problem that has these constraints? So it's super simple. I just do min, our classic trajopt formulation. I'm going to have, terminal cost. And then some state cost. Going to have the discrete time dynamics. And then I'll have it, whatever like other generic constraints I have. And then I'll just put this C of X. Did I say greater than or equal to 0? Yeah. So basically I can just add, since I'm already doing things in a non-convex way anyways, right? Remember, as soon as this is non-convex or these dynamics are non-linear, the trajopt problem is non-convex, right? And we have solvers that can solve this. So like using IPOpt, I can just add this as a constraint and IPOpt will just try and figure it out. And oftentimes it can. So I'll just add this nonlinear constraint directly into the trajopt problem. And now this brings me some sense of at least local optimality. So before I was taking there was maybe an optimal control, then modifying it to take into account the collisions. That control is no longer like the best way to go about moving throughout the system, given the constraints. But if I'm directly reasoning about these constraints, now there is that semblance of optimality again. And so let me now switch to, let's see, I have a demo where I did this. Let me pull it up. Okay. I'll stop this share just for a sec. Start this share right here. So I won't show everything and I won't post this code until after the homework's done because it does a lot of the stuff that you guys need for the homework. But basically what I'm doing is I'm just adding into, so if you guys have done questions 1 or questions 3 from the homework, you'll recognize this general framework. This is me using the fmin_con function. And what you'll see is that I have these collision constraints, which is exactly what I just wrote down. I have a list of a bunch of obstacles, and I'm just going to go through and add these collision constraints as a direct inequality constraint into the solver, where I say like, hey, the distance between these two spheres must be greater than 0. So like, don't let the spheres touch. And here the dynamics is just a double integrator. And then what we'll see is that IPOpt goes and it solves, this is not that crazy, like didn't take that long. And if I look at the actual resulting trajectory, I'm trying to get from the start to the finish, but I have to like move around all these spheres. And that's how it does it. And so each time I run this, it'll like regenerate where the spheres are. So let's try running it again, see if we get something interesting. Here's a new set of spheres. So you see how like, if I directly encode these collision constraints into the trajopt formulation, it'll reason about them and it will find me what is the optimal solution, acknowledging that these constraints exist. Does this general story of like, how do we include these constraints into a motion planner make sense?
Yeah.
Sweet. So now let me go back and I'll go through one. We have 15 minutes left. So I'll go through something that I have been working on the last like year or so that I think is super cool. You may not think it's cool, but it's basically everything we've done so far for collisions. I've just assumed that everything is spheres. And this is a super nice conservative approximation because this constraint is nice and differentiable. And so the whole, like everything we did is contingent upon this collision function being differentiable. We want to differentiate through our collision detection. We need some way to determine if these two things are in contact or not. And it must be like nice and smooth and differentiable. Like it can't just be like a 1 or 0. If it was like a collision oracle, it would just tell you 1 there's a collision, 0 no collision. What we want is that we want this like nice, we want some nice shape to it so we can tell like how far are we from a collision. Like are we like super in like, are the two spheres like really like touching or are they just like a little bit touching? So these are all things that we need basically to make the solver work with these constraints. Because remember, to solve these things with any of our like, optimal control tools where we're using like second order based optimization, we need to diff through this once, diff through this once, and diff through this twice. So everything here needs to be differentiable, including the collision constraints. And so what I worked on was this framework for computing this collision information between arbitrary convex shapes. So I'll give an example where this would be like tricky. So imagine if I had a, I'm not an artist. So imagine if I had a car and then I had like, a semi. So I have two big cars here. And say I wanted to do like motion planning for this like autonomous vehicle, I would have to approximate this thing using spheres. So, I could do, here's a few different ways people can do. I'll write down like I'll give you a few options. So you can do, I'll add maybe some spheres to the corners, and a big sphere on the inside. Do the same thing here. So I can just decompose this thing into a bunch of spheres. Or I can be super naive and just do like one big sphere and then one big sphere, right? So both of these things are not that great for a few reasons. This thing like dramatically over approximates the collision region. And this makes it like the resulting control would have to be so conservative that it would end up looking kind of stupid. And then on this side, we have like, a bunch of these constraints. So like, potentially like hundreds of thousands where we decompose everything into spheres. And this is still either over or under approximating. So, around these edges, this is over approximating, which is bad. And then also these regions are like kind of unfilled. So I could find some weird trajectory where like, some part of this hits some part of this, which, in this case might not happen, but is possible with other constraints. And that is not like that great for us. So if you imagine like this thing could hit, yeah, go ahead.
Just could you not like just have some kind of just a perimeter offset and just run all edges or corners. And then you have, I don't know, I mean, this is just an idea.
Kind of. So that's kind of what I'm about to get at, is that there's like a better way to take into account the specific shapes themselves and do this in a nice, smooth, and differentiable way. But as of now, spheres is like, this is what everybody uses. And so what I worked on is basically a way to compute the collision information between two arbitrary shapes. And so it's called DCOL. And what DCOL does is going to take two shapes, two convex shapes. Actually, I'm just going to share my screen on the computer because it will be far clearer. So let's see. So here's this paper. Basically, what we do is that we want, so it can be any one of these shapes. So here's an arbitrary polytope. So as many faces as I want to, so I could do like a cube or a rectangular prism, or any polytope I can describe with linear inequalities I can do here. And then a capsule, cylinder, cone, generic ellipsoid, and then this is like a padded polygon. So it's just like a 2D shape with like a cushion radius around it. So what I can do is I can take my robot or my system and I can decompose it exactly into these things. And then what I do is, I guess the videos are not going to be that good. So I'll hold videos here. So what we do is that we then solve for the minimum scaling that we have to blow these things up such that they actually like make contact with each other. So, you know, if it's not in contact, the minimum scaling is greater than 1. If it's in contact, the minimum scaling is less than 1. But all this to say, this is what happens under the hood. But what you would use is this Julia package here. And what you do is that you define your shapes. So whatever shapes you have in your system, you define that shape. And then you go through and you can compute the proximity. And the idea of this proximity is that greater than 1 means collision, less than 1 means collision, greater than 1 means no collision. And so this is all like laid out in the documentation here, but basically we do this proximity thing between these two shapes, and this will output if we're in contact or not. And it also includes a function that we can use to differentiate through this. So I can say for any two shapes, are these things in contact, are they not? And the cool thing about this is this lets you like directly consider like real geometries. So I think a compelling example is like this quadrotor example. So here is like a quadrotor going through an environment with a bunch of different shapes. And this is doing so optimally. Like I expressed all of these shapes as what they actually look like and go through and like actually solve it. Here's like a cone going through like a little hole in an opening. So these examples are problems that would be like much more difficult to solve if I just had to approximate all the collisions as circles. Here's like the piano movers problem. So I'm trying to move like a piano like through a corner in a hallway. This would be like really difficult to do with spheres. So there's a bunch of documentation. I'll like provide some examples, but basically if you're trying to do collision stuff and you feel like doing stuff with spheres is not going to work for your situation for whatever reason, that's totally fine. You can do everything you need to do with this package. And I have a bunch of examples, like all the ones you just saw, where we use this kind of thing. So with that, I think what else I want to cover. So I think that's a good stopping point. With the last few minutes left, happy to answer any general questions people have. Also happy to expand on anything that I went over that you feel like I could go over in more detail, or just general questions about kind of stuff that Zach's going over in class. So I'm all ears.
DCOL looks really cool. I'm wondering, why is it just convex primitives? Is it because non-convex ones are much harder, or is it because you can create non-convex shapes with convex shapes? Like
so, a good question. So the shapes have to be convex, and this is because the way the DCOL works is it forms like a smaller optimization problem that solves that minimum scaling. And this is a convex problem, and these shapes have to be convex. We scale them up and scale them down until there's a contact. So these shapes have to be convex. And what it results in is it's a super small, super fast problem to solve. And I can differentiate through this problem using some other like math tools and return nice smooth gradients. And then like just as you mentioned, This is not that big of a deal because in practice, I can just decompose my robot into a bunch of convex shapes. So if I had like, you know, a humanoid, I could just decompose this into a bunch of different shapes. You know, you have like, you know, a sphere, then like a cylinder, then like, you know, I could do like capsules, and then like, you know, say I want to use like a box. So again, not an artist, looks terrible. But the idea is that I can just take my non-convex shape, decompose it into a bunch of convex shapes, and then just use DCOL. So we just started with convex things because this is what makes the problem very easy to solve in terms of evaluating the constraint itself and being able to differentiate through it. But in general, this ability to write down these collision constraints, it works for non-convex shapes as well, because I can just compose a non-convex shape with a bunch of convex ones.
That's cool. Thank you.
I had a question about the control barrier functions.
Yeah.
So you showed how we could do collision avoidance if you just formulate the problem in full, like the constraint is the obstacles are constraints. How much faster is it to use a control barrier function versus sort of solving the full optimization problem? Is there a significant speed difference?
Yeah, so it can be like very, very significant. So I guess let's compare the two pipelines. So we have the CBF. CBF is going to be the following. It's going to have some box here. This is our like nominal controller. And this could be MPC, this could be anything. Normally we'll make this something pretty simple because we don't have to consider the collisions. So we'll think of something like relatively easy. And then this gets pushed through CBF thing, and then I get my control. And then we have constrained motion planning. And this is non-convex trajopt. So these are kind of like the two things I have to do. So in the case of CBFs, I compute my general controller, which can be something nice and fast. And I compute this, which is insanely fast because this is a QP where the size of the primal variable is the length of the control. So it's like a QP in 4 dimensions or like 3 dimensions or like 10 dimensions. It's never that big. It's a very small convex problem. And it has one constraint for each safety thing. That's a scalar constraint. And then bound constraints. So in general, solving this kind of QP, it's very small. Like you could easily do this in like, which somewhere between 1 and 4 microseconds. So this is 1e6, 1e minus 6 seconds. So I'll just say conservatively, this is like, if written correctly, this is always less than like 5e minus 6 seconds. So solving, putting a control barrier function on there adds such a small amount of computation. It's not even funny. Like it costs nothing to solve this problem because it's so small. So this could be convex MPC. Say this takes like a millisecond to solve because I'm solving like a relatively large convex problem. That's fine because it's convex. I know how long it'll take to solve every time. And I have guarantees for it won't take longer than X or it won't take a certain number of iterations. It should take in the ballpark the same amount of time. And then just adding this thing right here is very inexpensive. Costs us basically nothing. This, on the other hand, this can be, because it's non-convex, this can be crazy slow. This could not converge. This could converge immediately. It's so dependent on your initial guess and like the non-convexity of the problem and like how hard it really is that it's very hard to put any sort of like time guarantees on this. You basically just have to like do everything you can to make the problem as easy to solve and then just like exhaustively test it to make sure it still solves correctly. So this is like what like autonomous vehicles do this, right? They do this route. They do not use control barrier functions, or at least most don't. And so you can do this, but you have to be like aware that like there's some risk involved there that you have to mitigate through just a bunch of testing. Whereas this is like, at least timing wise, computationally is very easy to do. And this costs like almost nothing. Does that answer your question?
Yes, perfect. But then is the only downside to using CBF that you're just not optimal on your output? Okay.
Yeah, so like what you'll see is that like it'll sometimes do like kind of silly looking things. Because like it doesn't know anything, because like that formulation, all it knows about is a safety constraint. So it doesn't really know like how expensive it is to go like one direction or the other. Like I've put no information in that cost function other than just like try and deviate the control as little as possible. So it'll end up doing like some weird things. And also there's like a tuning parameter there. So if you remember the alpha, or sorry, the lambda that you saw, this is kind of like my like risk aversion. So remember, alpha has to be negative. If alpha is like very negative, so like -10, it's going to be like extremely conservative and it's going to like go super far around the obstacle, which is like silly looking. If I like lower it, it'll come a little closer, but it's like a little more fragile. So there's like a bunch of engineering trade-offs that have to come into like how you choose this parameter. But yeah, in general, this is like not going to be something that's optimal. It's not going to give you like the best trajectory given the collisions present.
Okay, makes sense. Thank you.
Yeah. And so what I'll do is after this, I'll post up some control barrier function code with a double integrator. And then after you guys turn in your homework on Wednesday, I'll post up the constrained motion planning example, just so you can see these ideas like in code.
Kevin, I also had some questions about sort of the formulation on the quadcopter that Zach mentioned in class with the quaternions and sort of plugging that into DCOL.
Sure.
Not sure if this is the right place to ask.
Was this is this the lecture yesterday?
No, this was like a week or two ago. I think lecture 15 or something.
So this was just his thing of like doing LQR and trajopt with quaternions.
Yeah. I was just wondering, does it extend to DCOL? Because I've tried implementing sort of the model that he had and sort of the dynamics that he had using the quaternions and then plugging that into DCOL. And it's coming out as non-dynamically feasible trajectories, but I suspect what's happening is the optimization's occurring over the quaternion incorrectly.
Yeah, so this is like very hard to get to work. So doing any sort of optimization over quaternions in a standard NLP solver is super difficult. The reason being is that it's going to apply all of those updates additively, not multiplicatively. So there's kind of like there's two main things that Zach did in class. One of them is like he modifies all of his gradients, Jacobians, Hessians, everything. They all get modified to account for the quaternions. And the second thing is that the way he performs differences and additions is he uses quaternion multiplication. And so if you put this kind of stuff into like IPOpt, it can do the first stuff. Like you can modify those gradients and everything for it, but it can't apply those updates to the primal variables correctly. So doing quaternion stuff in IPOpt is like a whole other story. And maybe we should tell Zach to like try and cover this because there are like hacky ways to get this to work. But oftentimes it's quite challenging. So like what we've done is that like in our lab, we have some solvers that like handle quaternions, but they're like a little rough around the edges. But yeah, like the stuff you're running into is like, I would totally expect that out of what you just described.
Makes sense. So what's the way around it? Is it change your parameterization of the orientation?
So what is the specific problem that you're solving?
So I posted on Piazza privately, but essentially trajectory optimization for quad rotor, and then we're trying to avoid spheres. So similar to what you showed.
Okay. Are you doing okay, each show is just double integrator. Yeah, that's like totally the way to do it. So doing everything as a double integrator and ignoring attitude, it's nice to decouple these problems. So solve the collision avoidance problem using a double integrator model, and then use LQR with quaternions to track that reference trajectory is like a nice way to kind of decouple it to take the quaternions out of the scene. Because in general, quad rotors are so well actuated that I can really give them any trajectory and it can follow it, right? Like I have such specific control over all my states that like I can give you a reference, and if it's like even remotely dynamically feasible, like the quad rotor can track it pretty well. So yeah, I'm just reading your post right now, totally doing everything as a double integrator. So like the example that I went over with those spheres that show up in the scene, doing that and then tracking it with a normal LQR for the with quaternions on the quad rotor makes a ton of sense. But I have to run right now, but I'm happy to tag up with you and respond to this Piazza post and maybe go in like more detail over.
Yeah, that'd be great. So, okay, sounds good.
All right.
Thank you.
No problem. I'm going to stop recording.